Good afternoon, students. This is elementary statistics 1401, and today is June the 13th. Today is Tuesday, and we are going to work on 5.3. Again, if you had any trouble solving the problems from 5.2, please email me clearly mentioning your class. I'm teaching 3 classes and give me the section number, problem number, and ideally a screenshot. Okay. And I will be happy to incorporate it in our discussion. You can always come and see me during office hours. My office hours are going to be right here at these links, 8:30 till 9:30, 2 days a week. But if this doesn't work out for you, you can schedule an appointment with me. Not a problem. So let me show you what the homework, where the homework problems are. Hopefully by the end of today, you will be able to do these problems. You should be able to do problems from 5.3. If you have any trouble with problems from 5.1, 5.2, feel free to ask. I'm here to help. All right, guys. So without further ado, let's get started. Now, these are my, sorry, opening the wrong notes. Okay, so these are my notes from chapter 5, page 3, right? Okay, I'm going to read it. I'm going to tell you what they're talking about. I'm going to give you some examples. Two events E and F are independent if the occurrence of event E in a probability experiment does not affect the probability of event F. Two events are dependent if occurrence of E and in a probability experiment affects the probability of F. Now, it sounds very complicated, okay, but let me give you an example. Do you think there is a link between probability of getting a 6 when you are um, tossing a die, or the probability of getting ahead when you're tossing a coin? You roll a die, toss a coin, but you get the point. So when you're rolling a die, the number you get has nothing to do with your tossing of a coin. These two events are independent. Okay? When two events are independent, all right, so let me give you an example before I go to the next slide or next definition from your text. So let's say we are rolling a die. These are the two experiments, probability experiments we are talking about. Rolling a die. Rolling a six-sided die. When I say roll a die, I mean six-sided, unless I say it's something else. Rolling a die and tossing a coin. Okay. Now I want to know, now I want you to tell me, if I say, what is the probability that you're going to get tail and a 6, a tail on your coin and a 6 on your die? So we say, and a 6 and a tail. Okay. So these are completely independent events. Okay. The probability that doesn't matter what you roll on your die has nothing to do with what you get on your coin. And those events are independent. If they're not independent, we say they're dependent. Okay. Let's look at the next one. All right. This actually, they go hand in hand. I'm going to save this here. What do they mean? What do they mean? Multiplication rule. Okay. When two events are independent, the probability of particular event and the second one, you find it. How do you find it? You simply multiply the two probabilities. Okay. Addition rule works for disjoint cases, right? We talked about addition rule in chapter 5, section 2, the previous class. We're talking about multiplication rule. And if two events are independent and you want to know the probability of getting E and F, you simply multiply. So let me give you an example. You're rolling a die and tossing a coin. Let's go back to something very simple, okay? So I'm asking you, what's the probability of getting a six and a tail? Find the probability of getting a six on your die and a tail on your coin. What's the probability? Clearly, these two are independent events. They have nothing to do with each other. Now you tell me the probability of getting a six when you roll a die is 1/6. There's six outcomes. I'm assuming it's a fair six-sided die. There's six outcomes. So you're going to say, oh, that's easy. 1/6 times, what's the probability of getting a tail? There are two choices, head or tail, 1/2. And that turns out to be 1/12. That's all this means, multiplication rule. Multiplication rule is associated with independent events. Okay, what does that mean? I know it put parentheses here, but you don't need the parentheses here. I don't know why it did. So let me get rid of the parentheses. I don't like it. It's a non-issue. Okay, and you can put a little plus multiplication sign here. That looks much better. So that's what we mean by multiplication rule for independent events. All right. What are independent events? When the events don't influence probability of one another. Okay. And it works for three events, four events, five events, doesn't matter. So let's solve a problem. For by the way, let me do this one. Let me work on this one here. Remember, I just told you it works for one events, two events. So if you have n independent events, like you're tossing a coin, you're rolling a die, you're drawing a card from a standard deck of cards, and you're talking about, let's say, you're rolling a die, what's the probability that you're going to get a six on your die, a king on your deck of card, and a head? So the probability of getting a six is 1/6. Let me write it down, okay? Probability of getting a six when you're rolling a die is 1/6. The probability of getting a king when you're drawing a card from a standard deck of cards is 52. And the probability of getting ahead is 1/2. And you multiply it just like you would expect. And whatever this turns out to be, I don't care. I can use my calculator, but you get the point, right? Um, whatever you get your final answer, it's your final answer. So this multiplication rule works for more than two events. Let's grab this problem from your book and see if we can work on it using what we have just learned. Okay, let's read the question. In a game of roulette, the wheel has slots numbered 0, 0, 0, and 1 through 36. So there are 38 equal or identical slots with different numbers, 0, 00, 1 through 36. So there are altogether 38. Keep that straight. A metal ball rolls around a wheel until it falls into one of the numbered slots. What's the probability that the ball will land in a slot numbered 21? Okay, so let's keep that straight. We're going to say the probability of landing on 21. We write it like this. The probability of landing on 21 is, now it's a common mistake. Don't write 1/36. It's 1/38. Okay, why 38? Why 38? because there are 38 slots. All right. So this is the probability of for one ball. You spin the roulette wheel, and there is a ball, and that's going to land on 21 only 1/3 of the time. That's the probability. But now they're saying you are doing it twice. Now, when you do it twice, you know these are independent events. The ball cannot remember where you want it to land, where it landed the previous time. The ball is going to land wherever it lands, right? So the probability of a ball landing on 21 is 1/38. Keep that straight. Okay. What's the probability that two balls will land on 21, one after the other in a consecutive manner? So let's write it down again nicely. What is the probability that the ball will land on slot 21 two times in a row? Probability of landing on 21 two times in a row. Two times in a week. Well, the answer is simple. It's 1 over 38 times 1 over 38. Okay? That's as simple as that. Why? Because the events are independent. They have no connection. They have no connection. Now, I will recommend if I give you a problem like this on the exam that you do this. 1 times 1 is 1. 38 squared is what? Is this number? That's your answer to this problem. Now, you're going to see, in math, things always get a bit more challenging as we move on. And you're gonna find some of the things a little challenging. So I would really encourage you to do the problems from chapter 5.2, 5.3. I'm going to solve a problem from your book, and you will probably find it a bit challenging. Okay, there's a lot of logic in this problem, and there is a problem like this that I have assigned on Blaze View on MATLAB. So stay tuned for something a little challenging. And the problem reads pretty simple. It sounds like a very naive problem, but it's a bit challenging. Let's read it. Compute the probability that at least one out of 1,000 aged 24 years will die the course of the year if the probability that a randomly selected 24-year-old male survives the year is 0.9986. Now, take a deep breath. Okay. So whenever you see this expression, at least in a math problem, especially in probability, stay extra alert. Okay. At least one means one or more. Okay. So compute the probability of at least one male out of 1,000. So one or more. One male could die, two males could die, three males could die, four males could die. You have to add all those things. It's very tedious, very tedious. But remember how we talked about um, complementary events? Okay, complementary events are what? From previous lecture, complementary events are two events. Okay, they cover the whole sample space and they are disjoint. They are mutually exclusive. They don't overlap. Okay, so bear with me a little bit. So what's going on here? So at least one male out of 1,000 aged 24 years will die. What's the opposite of at least one will die? Opposite of at least one will die is, opposite means complementary, is no one will die. Got it? So I'm gonna do this problem carefully, okay? I'm gonna say the event at least one dies. The complement of that is the probability that no one no one dies in that group. I'm just talking about that group. No one dies. Okay. Now, no one dies is the complement of at least one person dies. Out of 1,000, no one dies is the complement of at least one of the 1,000 men die age 24. We're going to come to the probability in a second, guys, but you really want to, let me write it down. Probability of these two events. Okay, let me write it down. Let me do a better job. And you want to reflect on it. E is the event that one dies, and F is the event that at least one dies. Okay. The claim I'm making is that E and F are complements. So if you take all the population, okay, and so you have no one dies and you have at least one dies. So these two will divide your sample space into two parts. And those are the two possible cases. At least one dies or no one dies. E and F are complementary. Let's write that down here too. Events E and F are complementary. Now, whenever you see at least, and I will give you problems like this, and there are problems like this on MATLAB, you will always find the complementary event and see if you can find its probability. I know we are supposed to find at least one dies, but remember the rule for complementary events. If you know the probability of one event, all you have to do is subtract it from one, and you'll get your right answer, so to speak. Okay? All right. So let's see. I'm going to keep these here because this is a difficult problem. I want to have it on the whole slide so that there's a little less confusion. So I am right now, I want to find that I have 1,000 people, nobody dies. All right, let's find that and then see what we can do with it. So what's the probability of no one dying? Dying. Let's just say no one dies. What's the probability that no one dies? Well, you have 1,000 people, and the question tells you the probability that a randomly selected person, we're talking about 25-year-old guys, men, survives that year is 0.969, sorry, probability is 0.966. Let me highlight that too. Let me highlight that too. The probability that a 24-year-old guy will survive the year is 0.9986, which you think is could be high, and it's high enough, but for me, but that's not the point. Now you're saying you have 1,000 person. The probability that person dies is this, and the second person dies is the same. And these are all independent events. Death, I'm assuming they're independent events, and the death, of course, two brothers could die together, something happened to their house. But let's assume independence. We're assuming we're making an assumption, okay? When I give you a problem like this, and that's why you want to listen to the lecture, okay? When I give you a problem like this, I assume that the probability that a guy dies has nothing to do with the probability that a second guy dies. Now, if you're in a war-torn area, the probabilities will be related. But we're not going there, right? So what's the probability that no one dies? Well, are you going to multiply 0.9986 thousand times? 0.9986 times 0.9986 times 0.9986. It'll take you forever, right? But you can do this. You can do this. It's the same, right? Multiplying 0.9986 a thousand times is same as 0.9986 raised to the power 1,000. Simple. That's much better. Your calculator will let you handle that, right? So I'm going to put this guy here, and let's see what my calculator does for me. This is what I'm getting, guys. Let me double check. I sometime entered the wrong number. I'm pretty confident I'm getting this. Okay, so I'm getting this. Double check. All right. What's the probability that at least one dies? Probability that at least one dies is going to be one minus that number. That's all there is to it. Okay, so that's much better, guys, right? That's much better. I'm going to use my calculator to find this difference. 2, 4, 6, 3, 5, 5, 9, 1. 2, 4, 6, 3, 5, 5, 9, 1. I can stick another 7, but I'm going to tell you the kind of trick I use. If you have this, Desmos, which is, go to Google, type in Desmos, and it's a good calculator. All you have to do is, and it works well with copy paste, because this long number, you're not going to enter it right, is that seems very high, actually. Take a look. So the probability that at least one dies is 1 minus 0.246355917, which turns out to be 0.7536448083. Got it? And that's our answer to this question. This is your answer. Let me highlight it. Now, so this problem is here, okay? So this is an example from your book, and it's right here. We got the answer. You have this example, but you really want to understand, okay? Which seems very high, which intuitively makes sense. Out of 1,000 people, even though the probability that somebody will survive is pretty high, 0.9986. The probability that at least one will die, at least one or two or three is this, which is pretty high, unfortunately. Anyway, I hope that makes sense. So we have a little bit of time. So what I plan on doing is I'm going to go to your homework packet and pick a problem and try to do it. Okay? And it's a hard problem, similar to this one. With me? So let's try it.